Okay, off we go. Here's where we were last time. We were talking about different things. We were talking about iterated intervals. We also talked about double intervals. Again, they're different, right? Now, one of the big punchlines of iterated intervals and double intervals is that, in fact, for sufficiently nice functions and sufficiently nice domains, which are pretty much all we're ever going to deal with, they always give you the same value, right? They will always be equal, but that is absolutely not the point, right? So you got to keep in mind the point is, how are they defined? What do they mean? And therefore, what connections can you make to other things, right? Again, I know I say it a lot, and I almost get tired of hearing myself say it, right? So I just imagine how tired y'all are hearing it. Y'all are of hearing me say this, but it's not about answers. It's about reasoning. That's what we're here for, right? So the fact that these are defined differently, importantly differently, is enormous, right? It's a huge point. All right. So, nevertheless, this is our little roadmap of how we do business, and not hard to persuade yourself that the way that you make your way through this roadmap as effectively as possible is first do that, second do that, and third do this. And so let's talk it through a little bit more carefully. The very first thing you're going to do with any application that you're going to solve with a double integral is you're going to take your application and figure out, what's the appropriate integrand, etc. But how can you write your application in question as a double integral? That's step number one. Right? A double integral is tailor-made to be really, really good at this. And we're going to do an example in just a moment. The second thing you'll do is recognize, just kind of doff the cap, to the fact that, hey, guess what? Good news. Double integrals can be computed by iterated intervals. Isn't that nice? Right? And then step 3, the plug and chug, what we've already seen some examples of is, you compute the iterated integral. After all, an iterated integral is really nothing more than single variable integrals kind of nested, right? And so the good old Calc 1 fundamental theorem of calculus, plug and chug. Okay. So, again, let me acknowledge, volume, I guess, kind of has a role in the sense that, I can compute it, in either of these two ways. That's how I know that these will compute the same things. At least that's what I think the most, geometrically satisfying take on why I know that those are the same. There's a more rigorous way to do that as well. It's just not as satisfying. To me. But don't make the mistake of thinking that you can make an argument about how to compute some application like mass by trying to make the case that it's the same as volume. It's at best a very awkward argument to try to make in a legitimate way. Okay, and of course, absolutely you can't do this. It just straight up doesn't work. Let me not overstate it again. It could be made to work, but there's a lot that has to get said to make that into a watertight, legitimate argument. So, what's the point, right? There's no benefit to that. Just follow the path and everything goes well. Okay, let's do one. Here is an application question, engineering related, let's say. We've got a rectangular sheet and mass is distributed across that rectangular sheet. How would I compute the total amount of mass? Right? Now we've talked about this problem previously, at least I've kind of I've talked about how you can't solve this problem, right? You can't just immediately say, hey, iterated integral. The pieces just don't fit together quite right. So here's what you can do, and I think this is a easy way to approach it. I can say, look, mass has this feature that the whole is the sum of the parts. I can chop this mass up into little pieces and compute the mass on each little piece. When you add up the individual pieces of mass, you get the total mass. It's a fundamental feature of how mass works, right? It's just, how could it be anything other than that, right? Now, I have a name for this that I like to use in recognition that not only mass, but many other quantities of interest have this feature, that the whole is the sum of the parts. It's really important. partly because so many quantities have this feature, but partly because many quantities do not have this feature. Right? So we need to make the distinction between those that do and those that don't. And I like the term accumulating quantity. The whole is the sum of the parts. I'm just going to call that an accumulating quantity. Yeah, you had a question. Sorry.
No, I just saw that I was going to ask if the triangle acts the same thing as the x, but I just saw right under it. It said.
Yeah. Okay, good. Yeah, good deal. Okay, so yeah, first recognition. Mass is an accumulating quantity. The whole is the sum of the parts. Yeah, sure. I think that's cool to write down. And then the next step, I mean, this is kind of just the definition of density. Density, when you have something distributed over areas, mass distributed over areas, density is the thing you multiply by area to get mass. That's what it means to talk about mass per unit area, which is how the mass is distributed. Right? So again, that's kind of immediate. No subtleties, no finessing, no making up concepts that may or may not actually be meaningful. Right? Just boom, right to it. And then lastly, we recognize, oh my gosh, look at this. Would you believe that is exactly the definition of a double integral? Oh, look at that. It's a 2-index Riemann sum, exactly what we wrote on the previous page or a couple pages back maybe. And so I can write that as a double integral. As a double integral. Okay, so you write that down. Now, by the way, I expanded this out to be as clear as possible as to what was actually going on in that argument. I don't expect you to write that down every time. All I expect you to write down is that if you've been asked to compute mass, then you can compute it with a double integral of density. If you just write that down, I'm happy. Right? No problem. Another little digression, momentary digression. We'll come back to the problem momentarily. We eventually got around to rewriting our deltas as d's, and we eventually got around to writing our limit summations as double integral symbols. You'll notice nowhere have I previously written, nor will I, that this is denoted by that. I didn't say that. Right? You look back at the definition, I have made no comment on what this by itself means. All I've got a definition of is that this combined notation means this. Right? So we don't actually technically have a definition of just that by itself, and we don't really need it. That said, everybody notices the pattern. Everybody sees what's about to happen here, right? And so it's a common and convenient and I think just useful little shorthand that, when you write down the beginnings of your Riemann sum, feel free to go ahead and just write that as a double integral symbol. It's not really. And again, I haven't defined this. And what I've written down in place of that, this thing here, I haven't defined that either. Right? That's not something that I've written down as a definition. There is no m-axis. Right? It's not a variable like x and y. It's a different thing. So this is a little sketchy, but you know what I mean when I write that, right? It's just a shorthand for a Riemann sum. And very common. Everybody does it. I'm all for it. Okay. So this development, you can instead sort of develop in this sort of parallel way. It's perfectly fine. Okay, let me pause real quick. How are we doing? Everybody on board so far? Yeah.
You'll always be given the width
You're talking about this right here?
The thing after it. The width and then it.
I'm not understanding. I'm sorry.
The word after width. They're like
the word after width? I don't see width.
It's not a word. It's a symbol. Like the density.
I'm sorry.
In the brackets with X and Y and everything.
The brackets with.
Yeah.
Oh, this right here. Yeah. You talking about that? Oh, it's the density. Oh, yeah. Well, if you're going to be able to actually compute one, you'll have to know the density. That's right. Anytime a student says always, I get scared because, you're asking me to make a promise, and I don't want to make promises unless I know exactly what I'm promising, right? So that's why I'm always a little hesitant there. But certainly, if you're going to compute an integral, you do need to know what the integrand is. Yeah. Totally. Okay. So mass. Oh, I'm sorry. You had a question. Yeah.
Yeah, I was just, I guess I'm having a hard time understanding the first, limit, the sum of delta M.
This right here?
Yeah, kind of what's the domain that we're talking about, and why is it change in M and not the mass itself?
Okay, so this is our domain. We've got a rectangle. And all this says, when I say summation delta M, I just mean I'm going to take that, here's my rectangle, I'm going to chop it up into little pieces, and on each little piece, I could ask, well, how much mass is in that little piece? That's what I'm going to call delta M. And then I'm just making the observation that if I add all of those up over the whole rectangle, that's what that means. Then I'm just making the recognition that the whole is the sum of the parts. Now, I don't really need to say limit for that to be true, but I'm saying limit because I'm eventually going to need the limit because I'm eventually going to want to write this down as a Riemann sum. Is that satisfying?
Yeah.
Good. Okay. So what we just did up here, this is our step one. We've taken our application, we've written it as a double integral. And then we're going to proceed to step two. I'm going to acknowledge that double integrals can be computed with iterated integrals. So, boom, right? Nothing to it. The only little detail, don't forget you do need to know the bounds, and the shape of the domain tells you the bounds for x and y, which go there. That, details. Okay, and then lastly, plug and chug. Let's see here, up here. Last thing we're going to do, but compute with the fundamental theorem. And I didn't write that down here because, again, we've already done that. And that I could make up a density function. You would have to know the density function to be able to, finish this off. But that's getting us into algebra that we've already talked about how to do. So I just want to keep this streamlined. Okay, so again, I wrote down a bunch of stuff here for the purpose of being expansive and communicative. In practice, all I actually expect, or I'll say all I require that you write down on this is that mass is a double integral of density, which is computed with an iterated integral, and then, you do have to, plug and chug down to an answer. All right, now let me come back to the diagram. Let me remind you that, I made this observation last time that, you really have to, you got to give me the double integral, otherwise it looks like you're making this argument here, which of course doesn't really work. So how much does it cost us? How much does it cost y'all, right, that I'm requiring you to write down the double integral? Look how little it costs you. It's just colors. It's just that right there. Just give me that, right? And that makes it clear that you are making a double integral argument that's mathematically reasonable, right? And it distinguishes you from some students that are going to actually try to make an immediate iterated integral argument. It really doesn't work. It's got a lot of holes, a lot of gaps. All you got to do is write this down, and you're defended against that bad impression. Does that make sense to everybody? See what a small ask this is, right? I think this is really important, just from a completeness standpoint. Okay. All right, so that's the process. This example here is just a recognition that double integral notation is very convenient. So this little bit that I did here, writing this instead of that, is kind of a convenient shorthand. And here's a sort of another example of another way in which that can be really convenient. I don't want to go through all the details of this example. Y'all can read through the other stuff at your leisure. The big idea is that we've got a bunch of materials on the ground level here, bunch of bricks basically, and we're going to try to build a wall. And oh gosh, I mean, every time I want to put a brick at this spot on the wall, I got to bend or I got to pick up. They're heavy, right? I got to. There's a certain amount of literal work that you have to perform to be able to pick up the bricks to the height that they're going to be in the wall. And no big deal. You pick up a brick, whatever. Okay, if that's a big wall, it's a lot of work. It's literally physics work, right? You're picking up a tremendous amount of weight. A non-trivial distance. It's a workout, right? And when you do a lot of work like that, it's kind of satisfying to be able to compute exactly how much work did you just perform, right? I just executed 15,000 foot-pounds of work, right? So if you have to build a wall like this, how would you compute that? How would you decide how much work it took to do it? Well, I argue as follows. Work is an accumulating quantity. Now let's think that through for a second. There's a certain amount of work it takes to put that one brick in that one spot right there. And there's a certain amount of work that I have to execute to put the brick that's going to be on top of that one, right? And if I know how much work it takes to do each individual brick, if I add up, I get the total amount of work, right? So again, the whole is the sum of the parts. It's just the way of the quantity in question, yes.
Doesn't it take more work to go to a higher level?
Absolutely, and we're going to recognize that in just a second. That's coming up momentarily. Absolutely. So the whole is the sum of the parts, and let's see here. So now let's look at each individual part now. I want to look individually, one brick at a time. How much work does it take to get that one brick where it goes? And here's how we deal with that. It was on ground level, and then I had to lift it up a certain distance to get it up to where it's going to eventually be, right where I'm putting it. And grand total work is force, namely how much does the brick weigh, times distance. How high did I have to lift it up? Well, it was at ground level, y equals 0. I'm lifting it up to some location x comma y. It's at height y, so I have to lift it a distance y. Yes.
Would the Earth still stand if we use the x perspective? So rather than evaluating like dy dx, do dx dy, and then start with the x as a constant?
That's the nice thing about starting with a double integral is there is no distinction. Right? If you're talking about a double integral, I mean, when I write down this double integral, I haven't even started thinking about x and y yet, right? So we're going to write the double integral down first. And then once we've got the double integral written down, then I can start deciding, what would be the easier way to compute this, right? I don't have to think about that while I'm developing the double integral. Maybe I misunderstood that.
So the y df, is our first step regardless if we're starting from dx dy.
Yeah, absolutely. Because from a physics standpoint, x is irrelevant.
Okay.
Right? Now, from a real world standpoint, oh gosh, if there's a pile of bricks over there and I need to turn that into a pile of bricks over here, yeah, still a lot of work, still backbreaking. From a physics standpoint, there's zero work there. So if you want to document all of that, the horizontal element of the effort, I don't want to call it work, but the effort, then that's, I don't know how to, that's not really something we're armed to deal with. Yeah.
I just want to check, I understood the density equation. It's pretty much saying the farther you go to the right and up, the more dense.
Yeah, so this is a weird wall. Yeah, so this is a wall where it's not very thick here. Maybe we're using, maybe it's just very sort of, not a very deep, thick wall, and then the more we go over this way, by the time we get up there, it's bigger and thicker. It's a distraction, right? But I just wanted to keep it from being constant, and so yeah, whatever, right? Okay. All right, so fine. So you see, work is force times distance, so we write that down, and now let's look at force. I mean, how much does that brick weigh? Well, we know what the density is. And weight is, and of course, my pen chooses this time to die. Weight is weight per unit area times area. In other words, how big, what's the area of that little spot in the wall? Right? And so again, that's, presumably how this density function came to us. This is, weight, not mass, weight, right? Force, pounds, per unit area of wall. Okay. All right. So now, what's the point to all of this? I mean, why are we doing this example? What's the takeaway? The takeaway, we could have, and arguably, if you want to get real rigorous and real careful with your notation, arguably, maybe we should have written these down as, all of this should have been written down as Riemann sums. A case could be made. But I'm using this shorthand notation. I'm using this, very convenient, you know what I mean when I write the integral notation. I just mean the corresponding Riemann sum. And so, yeah, sure, go ahead. Much more compact, much more convenient, and gets you to the same conclusion, and perfectly fine and dandy. Everybody does it. I'm all for it. Okay. All right, y'all can read the rest of the details if you care. So, new concept that we have to worry about now. This is potentially difficult situation. Everything we've done so far, the domain that we were looking at was a rectangle. We've only talked about rectangular domains. Yeah.
Sorry. I just had a question about the previous slide.
Okay. Yeah, so conveniently, so I bypassed that problem by giving density. I didn't write this down, but my intention was that density is weight per unit area, not mass per unit area. So this word density can mean different things in different contexts, right? So it's sometimes thought of as being mass per unit volume, but in general, it's stuff per unit size. And the stuff that, just to avoid having to deal with gravitational acceleration, let's just go ahead and say it's given in pounds. Yeah. Is that cool? Is that satisfying? Yeah. Cool. All right. Okay, so non-rectangular domains. What do we do? Oh my gosh, everything we've written down previously crashes and burns. It doesn't work. That was only for rectangles. Well, here's the good news. Here's my non-rectangular domain down here. And we'll start as we did previously with the question of computing the volume under a graph. So here's the surface sitting above that non-rectangular domain, and I want to compute this volume. Let's see here. The volume of a loaf of bread. I don't really care what the footprint is for the loaf of bread, but the volume of the loaf is the sum of the volumes of the slices of bread. You can chop it up into slices. All good. It's still a slice of bread. It's still got a volume that's area times thickness. The area is still the area under a curve. The area under a curve is still an integral that you can compute going in, as I've drawn it here, in the x direction. Everything works still. Almost everything's exactly the same. This is fabulous news, right? Great news. The one little detail is that our bounds are now not constants. And you can see this in the picture as follows. For one value of y, as we compute that cross-sectional area, the starting value for x will be that value, let's say. But then look at a different value of y. Maybe I choose this value of y instead. Then I'll only be moving something like that. meaning that my starting value of x is not the same. Now my starting value of x is over here instead of over there. So the starting value of x, my lower bound for my x integral, depends on which y we're looking at. Everybody see that in the picture? So, okay, no big deal. I just have to recognize that this lower bound is a function of y. Now again, it's, oh my gosh, scared, creepy, bounds are allowed to be functions, oh my god, right? Is that okay? It's perfectly fine. Because don't forget, while you're looking at that inside integral, right, here's my inside integral, for the purposes of that inside integral, the outside variable is constant. Right? Which means, while that is a function of y as far as the y integral is concerned, as far as the x integral is concerned, that's still a constant. Does that make sense to everybody? So it's not even the fact that it's a function of y won't even show up. It won't influence anything until we get to the y integral. So no big. All right. So let's see here. Let me get back to the right size here. There we go. Oh, and then here's another piece of good news. This picture that I drew, and then the subsequent picture of the slice, and doing my development, figuring out how to write down this integral, thinking about, wait a second, how will my bounds depend on y? What part of this picture did I really need to conclude what I algebraically want to get written down? And the answer is, I only need to look at the domain. Right? So everything that I need to know about this is just in the domain itself. In particular, I just need to know how do these edges curve around, because those edges, this purple edge right here, that's the curve that when you give me a y, I'll look at the corresponding point on that curve, see what the corresponding x coordinate is, that'll be my lower bound. I only need to see that curve. In particular, that's part of the domain itself. Notice the verticality of this, irrelevant, right? The verticality of the picture, right? The up is only relevant to what will eventually become the integrand. And I already know what the integrand is. I don't need a picture to help me understand the integrand. So, in practice, when you do these, we don't draw pictures that look like this. I don't need to draw that at all. You just draw the domain. Right? And again, I can see everything that I need by looking at just the domain. And so now with the above picture in mind, let me remind you of the argument. I can look, for example, at this curve, and then for a given value of y, I can look at the corresponding point, which tells me how x will vary. This is sort of the starting point for my x integral, and I can see that lower bound for my x integral, what that's going to be, and algebra ensues, and we'll talk about that in a moment. But notice, this is the only part of the picture I actually use. Right? All the three-dimensional stuff, irrelevant. Big savings, big conceptual savings. Three-dimensional pictures are hard to draw. Right? They're time-consuming to draw. Two-dimensional picture is much easier. So it's a big insight. You only have to draw the domain. And then the last observation before we start getting into some actual examples. When you want to know a bound, you want to find a bound? Okay. That bound is going to come from a point. That point you're going to identify because that point is on a certain curve, which of course has a certain equation. And all you got to do to find this bound is just identify that bound corresponds to a point on which curve, write down the equation of that curve, and then solve for what you're interested in. And very important, this is subtlety here, but what you're interested in, we're looking for an x bound here. So you solve for the variable whose lower bound, in this case, you're actually interested in. So don't forget, little delicate detail. Solve, yeah, but solve for x if you're looking for an x bound. Let's do one. Okay, in practice. Here we go. Suppose our domain is this triangle. Now, why are we interested in this triangle? Whatever. Who cares? Don't worry about it, right? So for whatever reason, we're computing this double integral. Maybe we're computing the amount of mass in this triangle, and x plus y is mass per unit area. Maybe I'm computing the volume sitting over this area in some direction, whatever, right? Don't get distracted by where did this double integral come from. Let's assume we're interested in this double integral. So, let's see here. It would appear that we've decided, and by the way, this is arbitrary. You can do these in either order, but for just to get the ball rolling, we're going to start by doing dy on the inside, dx on the outside, right? And so that means as I write down my first development of the integral, I need to know the range of values of x, and x, I'm going to have, let's see here, I'm going to be starting at, colors, I'm going to be starting at that value of x. I'm going to be ending at this value of x. And now you can look at your picture. Sometimes it's just easy from the picture. This is what I'm going to call a freebie. A casual glance, I can see exactly what the x bounds are because I know exactly where these two starting and stopping points are. Just looking at me in the picture, the starting value of x is clearly 0. Because it's at the origin. The origin has x equals 0. And the ending value of x is where x is 1. How do I know that? Well, because these coordinates of these points were given to me. And the x coordinate of that last slice is where x is 1. Okay, here's where it gets interesting. Assuming now a particular value of x. So we're going to assume that for that value of x, we're looking at this x slice. That means a slice perpendicular to the x-axis. Now I want to know my starting and ending values for y. Okay, well, y starts at this point. And I want to go through this process. I'm going to understand bounds by looking at the corresponding points. I'm going to identify what curve they're on. I'm going to then identify the equation of that curve, and then I'm going to solve for what I need. So let's go through that process here. That point, defining my lower bound, that point is on that curve. That curve has that equation, right? The point is on that curve with that equation. Let's see, wait a second. What am I doing? What am I trying to solve for? Why am I here? Apparently I'm trying to figure out y bounds. I'm looking for, as I go up this x slice, I want to know where does y start. So let's not lose sight of the fact that I need to solve for y specifically then in this equation, and thank God that's super easy. That y bound then is 0, and so that lower bound for x, lower bound for y is 0. Let's do the upper bound. Very, very similar. Okay, again for a given value of x. There's where I stop my y slicing. Right, trying to understand my y slicing. So let's see here. Well, that's where I stop. That's the point. That point is on this curve. It's not on this curve anymore. Forget about that curve. Right? So we're looking at that blue curve. That blue curve has this equation. Where did I get that equation from? Well, I had to do a little bit of legwork. I had to look at the curve and realize it goes from that point to that point. I had to realize that those points were given. I had to remember all of my high school algebra, blah, blah, blah. Right? So details. You're always going to have a certain amount of legwork in having to sort of put together these kinds of details. But anyway, the point is we identify that equation. We take a moment to recognize what I am looking for. I'm looking for my ending value of y. Right? Y, therefore, is what I need to solve for. So, very common mistake. In this equation, I need to solve for y. I need to write y as a function of x. So, solve for y as a function of x. Now, again, the algebra is easy. Just make sure you solve for the right thing. This formula right here, x. That formula x is the formula for y as a function of x. And a common mistake, I see the following mistake all the time. It's so common. I see students write the upper bound as y. Because, well, there it is. And then y, x, y, what's the difference? They're the same. I'll just put y instead of x. It makes no sense. Right? It doesn't make any sense at all to say, hey, for a given value of x, I want y to stop when you get to y. Doesn't make any sense at all. Does everybody see that? So, be careful. Make sure you solve for the right thing and that you write your answer in terms of the right thing. Yes?
Is there a particular reason why DLAC was first?
No, that's a great question, and I'm going to do it the other way in just a second. This was just to get the ball rolling, just a first example. So arbitrarily, I chose this, and now we're going to do it the other way. So the important part of this argument is we have now turned a double integral into an iterated integral, and you'll notice that everything else over here, this is just plug and chug, computation. We've already done a bunch of that. Okay, let's do it the other way now, just to mix it up, just because we can. Same shape, same double integral to start with. Who knows where it came from? Okay, this time we're going to slice it the other way. dx dy. Okay, so thinking it through. Okay, starting off with, let's see here. What is the range of values for y? Well, slicing perpendicular to the y-axis. My slices now look like this. And let's ask, where's the first and last? Well, my first slice, my first slice, of course, is that one. My last slice is going to happen at that point right there. Again, sometimes the fish just jump in the boat, and this is another one of those cases. If I want to know what's the value of y on that curve that's clearly where y equals 0, then yeah, it's not a lot of solving necessary. It's just where y is 0. And then likewise, how do I solve for how do I solve for y at this point? My last y slice, well, that point's y coordinate was given as 1. So, freebies, you take your freebies. Now, again, we're going to focus on a fixed value of y. There, I'll use a different color for this. There, for that value of y, that's how x is going to vary. X starts, my starting value of x, keep in mind we're looking for x, starts at that point. That point is on that curve. Thank you, picture, by the way. Notice, I need the picture. The picture is what tells me which one. I've got 3 lines here. Which one do I solve to see what my bound is? Well, you got to let the picture tell you which one is the one where your lower bound actually starts. Right? You got to have a good picture. Okay, so point on that curve. That curve, again, high school algebra from the givens has that equation. Again, don't get yourself mixed up at the very end. It's super easy to get mixed up at the very end. We got to remember, what are we trying to find? We are trying to find an x bound. We're looking for a lower bound, right, for our x integral. So in this equation, now I have to solve for x. The formula for x as a function of y is now y. It's not x. Right? I need x as a function of y, and that formula is y. Is that cool? Okay. And then let's do the upper bound. Let me get rid of the okay. All right. So okay. So for my upper bound again, this is an x bound. I want to know the ending value of x as I move along that slice. It ends when I get to that point. That point is on this curve. This curve has, well, again, an easy equation, basically given, right? Again, very importantly, though, don't lose track of what you need to solve for. I'm looking for an x bound, so in this equation I solve for x. And again, sometimes that's super easy. And this is what you get, and therefore that is your upper bound for x. Yeah.
If you were given the second point, would you be able to plug in the one from the other, from the outer?
If you're given what now? I'm sorry.
If you were given the point, could you plug in the one from the outer integral into your equation? Because you know y will only go up to 1. So
it sounds like you're talking about a different example, and I don't think I can answer that without understanding all the specific parameters. So let's talk about that after class, and we can write down the exact details and go through it. Yeah, cool. All right. Okay. Here's another example. This is actually two examples. There's a moral to the story on these two examples. I'm going to skip to the moral part. So I'm going to leave it as an exercise for y'all to do the first half of this. I claim that if you do dy dx for this domain, this region here, bounded by those two curves, well, let me broad stroke it for you. So x, right, our x slices that look like this, x is going to go from -2 to 2. Now you're going to have to do a little bit of algebra. You're going to have to look at the picture, think about which points and which curves intersect and solve, etc. But x will go from -2 to 2. And then for a given value of x, let me just clean up the picture. For a given value of x, y is going to go from here, which is on this curve, which has that equation, solve for y, to here, which is on that curve, which has that equation, solve for y. And so you get those bounds. I did that quickly, right? Make sure you're comfortable with the details, think it through. Not only make sure that you believe me when I do it, make sure that you can do it, right? First principles. But let's do it the other way now. Here's where things get a little weird. Let's look now at if I do the differentials in this order. Now, seemingly nothing particularly scary about this. I've got a non-scary looking shape, and who cares if I do x first or y first or whatever, right? It does not seem like things are going to get weird. Let's go through the process. Y is our first thing. Y is going to start there. Our y slices look like this, and our y slice ends there. And we're, again, sort of easy geometry. The lower bound for y is 0, and the upper bound for y is one of the given curves. It's 4. Okay. So the interesting part is in when I fix a value of y, we look on this y slice, and I want to know, what does x do? What's the range of values of x as I move across for that value of y? And let's go through the process very carefully. my lower bound for x comes from starting at that point, which is on this curve, which has that equation, and so many students, oh my gosh, so many students will say, oh, that curve is x squared, and they will put x squared as their lower bound. It's dramatically wrong. It doesn't make any sense. It's just garbage, right? You got to remember the relevant detail. What we are doing here, we are trying to find a lower bound for x, right? This coordinate we're interested in is a value of x. You've got to solve for x in this equation. And when you solve for x in this equation, you don't get x squared, right? You solve for x in this equation, and you're going to get either plus or minus the square root of y. Does that make sense to everybody? It's so easy to fumble on the 2-yard line here, right? Don't fumble on the 2-yard line. X squared, garbage answer. Got to solve for what you're actually interested in solving for, so you're going to get plus or minus square root of y. Now, which one do you get? Well, again, the picture is going to tell all. This lower bound that I'm looking for, is this a positive or is it a negative? The picture makes it pretty clear, I think, that this is a negative. And so that's why we take the negative of our two options. How are we doing? Everybody with me? Okay, it's a significant landmine. A lot of students get this wrong. And again, your bridge falls down. This is not a mathematician fussiness, right? You will get garbage nonsense answers. Okay. All right. Okay, likewise, the upper bound is now a little easier because we've kind of been down this road. So let me go a little bit more quickly. The upper bound, again, we're interested in an x value. It comes from that point. That point's on that curve. That curve has that equation. Oh my gosh, it's the same equation. That's a little weird. Right? Upper bound and lower bound come from the same curve. Whatever. We're interested in solving for x. Solve for x. Choose appropriately. This is clearly a positive x coordinate, so we take the positive square root. Everybody happy? Okay. All right, so here's the takeaway. I said this example has a moral to the story. The moral to the story is one of these options is better than the other. And you should choose the one that works better, that makes your life easier. Of course you should, right? So between these, which one would you rather deal with? I have a strong preference myself. I would much rather deal with this one. I don't like square roots. And let's be clear about how bad this could be. It's tempting to say, well, whatever. I mean, the square roots are in the bounds. You just plug in the square roots at the end, right? But wait a minute. What you're computing here, this dx integral, more to the point, the inside integral here is the integrand for the dy for the outside integral. So if you have square roots in your inner bounds, they're going to be in your outer integrand. And I hate it when square roots are in my integrand. Those integrals are hard. That make sense? So there's a strong preference here. Now, how do you tell? How do you avoid doing it the hard way? And do I have to write it down both ways every time and based on that choose? I can't promise you that you won't have to in some circumstances, but there is a pretty good general broad stroke rule that works surprisingly well. And that is, notice the problem came up when I had to solve for x, right? It was the fact that I had to solve for x here. That's where the square root came from. Now, I don't want to have to solve for x. I like solving for y in this equation, right? So you can just look at the equation. In fact, you don't even have to have drawn the picture. You can see right here in the statement of the question, well, this curve is probably going to be relevant. At some point, I'm going to have to either solve for y as a function of x or x as a function of y. And immediately, you can just look and see, oh yeah, I'd much rather solve for y. right? So choose your slicing in such a way that you'll have to solve for the thing you want to solve for. Does that make sense? It's just, kind of strategic thinking. Okay. All right, there's a similar example here, and I am not going to have time to get through it, so that's a shame. We'll draw the line right here. We'll learn another nice moral to a story next time. See y'all later. Have a good one.